The life of a star. Stars exist because of a fragile balance. Gravity pulls their enormous masses inward, millions upon millions of trillions of tons of hot plasma, while deep inside, fusion pushes back. In the heart of every star, hydrogen atoms are squeezed so tightly that they fuse into helium. This process releases a flood of energy, light, heat, and radiation that pushes outward, countering gravity's endless pull. For millions, even billions of years, this balance holds steady. The star burns peacefully, shining as a beacon in the cosmic dark. But eventually, its fuel begins to run out. When the hydrogen is gone, a medium star, like our Sun, swells into a red giant, fusing helium into carbon and oxygen before slowly cooling and fading into a quiet, dense ember, a white dwarf. But for stars much larger than our Sun, the story takes a darker turn. The collapse begins. When helium runs out, gravity starts to win again. The core collapses inward, temperatures soar, and new rounds of fusion ignite. Carbon burns into neon over centuries. Neon fuses into oxygen in just a year. Oxygen transforms into silicon over a few months. And finally, silicon fuses into iron in a single day. And then, everything stops. Iron is the end of the road. It's nuclear ash. It cannot release energy by fusion. Without the outward pressure of fusion, the delicate balance collapses. Gravity, relentless and merciless, takes full control.
Supernova, the final breath. The star's core begins to implode. Protons and electrons, crushed under unimaginable pressure, merge into neutrons. In a fraction of a second, an Earth-sized iron core shrinks to the size of a city, a sphere of pure nuclear matter. The rest of the star follows, falling inward at nearly a quarter the speed of light. Then, it hits the core and rebounds. The result is a cosmic detonation, a supernova. In that instant, the star unleashes more energy than our Sun will emit in its entire lifetime. It outshines entire galaxies. Its outer layers are blasted into space while the dense core remains behind. The birth of a neutron star. The neutron star, matter beyond imagination. A neutron star is tiny, about 20 to 25 kilometers across, but unimaginably dense. It packs more mass than the Sun into something the size of a city. Just 1 cubic centimeter, a sugar cube's worth, weighs over 1 billion tons. That's the mass of Mount Everest, compressed into a coffee cup. Its gravity is second only to that of a black hole. If it were any denser, it would become one. Light bends around it, allowing us to see both its front and part of its back at once. Its surface blazes at over 1 million degrees Celsius, while magnetic fields twist and roar with unimaginable power. But as extreme as the surface is, what lies inside is even stranger. Inside the star of neutrons. A neutron star is like a planet made of nuclear matter. It has a hard, solid crust above a liquid core. But the materials it's made of defy all logic. The outermost layer is made of tightly packed iron atoms, remnants of the supernova, locked together in a crystal lattice with a sea of electrons flowing through them. Deeper down, the pressure rises. Nuclei are forced closer together. Protons merge with electrons to form neutrons, and the matter becomes more and more exotic. At the base of the crust, things get bizarre. Nuclei are squeezed so tightly that they start to merge into one another, forming long rods, sheets, and tangled shapes. Physicists call this nuclear pasta, matter shaped like spaghetti and lasagna, made of protons and neutrons. It's so dense and rigid that it may be the strongest material in the universe, millions of times tougher than steel. Even the mountains on a neutron star's surface, barely a few centimeters tall, can be more massive than the Himalayas. Beneath that lies the mysterious core. Here, the density is so extreme that we don't fully understand what happens. Protons and neutrons might dissolve into a soup of free quarks, a quark-gluon plasma. Some of those quarks might even transform into strange quarks, creating a new form of matter, strange matter, a substance so exotic we can only theorize about it. No one knows for sure, and that mystery is what drives astrophysicists to keep exploring. The spinning corpses of the cosmos. When neutron stars are first born, they begin to spin rapidly. Like a figure skater pulling in their arms, they conserve angular momentum, spinning faster and faster until they rotate many times per second. Their magnetic fields are the strongest known in the universe, a quadrillion times stronger than Earth's. These fields generate powerful beams of radiation that sweep across the cosmos like cosmic lighthouses. Every time the beam passes Earth, we detect a pulse. That's why we call them pulsars, rotating neutron stars flickering in the darkness. Some are even more extreme, magnetars, neutron stars with such intense magnetic fields that they can distort atoms, rip apart molecules, and crack their own crusts with bursts of energy so powerful they can be seen across galaxies. When two neutron stars collide. But the most spectacular chapter comes when two neutron stars find each other. Bound by gravity, they spiral slowly inward, losing energy through gravitational waves, ripples in the very fabric of space-time. As they draw closer, they accelerate, until in one blinding instant, they collide. The result is a kilonova, an explosion so powerful that it forges the heaviest elements in the universe. Gold, platinum, uranium, the materials that make our jewelry, our electronics, our civilization, were born in the death throes of merging neutron stars. Stars must die not once, but twice, to give the universe its most precious elements.
The cycle continues. Over millions of years, the dust and debris from these explosions mix back into the galaxy. Gravity gathers it again into new clouds, new stars, new planets. Our solar system was one of them. Every atom of gold in your ring, every bit of uranium in the Earth's crust, every trace of heavy metal in your body was once part of a neutron star that lived, died, and exploded billions of years ago. We are made from the ashes of stars, the remnants of long-dead giants sent across time and space to become part of us. Closing. So, the next time you hold a piece of gold, look up at the night sky and remember, that metal was born in a collision between two dying stars, in a flash so bright it outshone galaxies. Stars had to die so that we could exist. The atoms that form your body were forged in the hearts of suns and tempered in the death of neutron stars. We are the universe, made conscious, born from the ashes of the cosmos. And that is pretty incredible.